All right. Oh, yep, we're live. There we go. All right, so like I said before, several of you got in here. This is not a C++ talk. If you're hoping for a C++ talk, it's okay if you run across the road real quick. I don't think it's raining real hard out there. But this is why data access patterns have always mattered. It's some historical perspective, something that I've been thinking about lately. It kind of has been bothering me, so I put together a bunch of notes. My name's Jason Turner, and just for the record, I have stickers up here. If anyone wants stickers, you can come get them afterward, or I might give one to you if you ask something or say something particularly interesting. Host of C++ Weekly, I've been releasing YouTube videos for 394 weeks straight. Makes me question some of my life choices, but 7 years now going on. And I just got 100,000 subscribers a few weeks ago. Very exciting. Silver play button underneath my desk because there's nowhere else to put it. Microsoft MVP since 2015. Just out of curiosity, does anyone else have an MVP that's in the room at the moment? No? Okay. I know there's other people here. I do code reviews and on-site training for C++ specifically, but sometimes things like this will come up. I also pace a lot, so they adjusted the camera for me for those of you who might be coming in remotely. Okay, so my talk is different from most of my other talks. Interestingly, I realized the last time that I said that was the last time I presented at Techtown 2 years ago, remotely as well. I don't normally use this presentation system, so hopefully everything works out all right. And this is not a C++ talk. And I don't have any specific point that I'm trying to make. I previewed this talk at my meetup. Do you go to your local user group meeting of any sort? Good, more of you should be raising your hands. I previewed this talk at my local user group meeting, and they're like, that was a good talk, but what was your point? And I'm like, I don't know if I actually had a point. I just wanted to give some historical perspective. Then they're like, okay, then it was a good talk. All right. I just want to make you think a little bit. That's my goal today. But don't worry, we will get a little bit of C++ and a little bit of 6502 assembly on the screen. Does that make everyone feel better? No? Why not? Who's familiar with 6502 assembly? I'm going to be calling on some of you to read some of this stuff up here then. All right. So if you're like me, I graduated from university in 2000. I started in 1996. And I'm thinking about like data structures and algorithm analysis and such. I kind of walked away with an impression that somehow linked lists were better than, say, arrays or vectors. Because, you know, when you do an analysis of the operations, inserting something into the middle of a list, that's cheaper, right? Okay. So I used list instead of vector by default in my code from the first probably 5 years that I was a C++ programmer. And we're talking, so if you're not a C++ programmer, standard list is a doubly linked list. Vector is a contiguously allocated chunk of storage. My code worked, and there was no problem with this, right? I used list, it worked, fine. And one day I come across something like this from Bjarne. This is from Bjarne Strustrup's FAQ. It says, "Are list evil? According to some corners of the web, I am under the impression that vectors are always better than linked list and that I don't know about other data structures such as trees and hash tables. Obviously, that's absurd. The problem seems to be an interesting little exercise that John Bentley," does anyone know who John Bentley is? No? Has anyone ever heard of the book Programming Pearls? I'm almost positive he's referring to the author of Programming Pearls, which is a very popular book at one time. It's a lot of like code optimization kind of exercises in a lot of ways. Says insert a sequence of random integers into a sorted sequence, then remove those elements one by one as determined by a random sequence of positions. Do you use a vector, the contiguously allocated sequence of elements, or a linked list? And he has other links in here. You can go find this URL if you're interested in doing that. He says, note the absence of list and vector in the conclusion. Don't confuse an example with what the example is meant to illustrate. So let's get to the point here. I missed something, unfortunately. Don't store data unnecessarily. Keep data compact and access memory in a predictable manner was his conclusion here. He says, my impression is that many viewers fail to understand that the purpose of this example is to illustrate some general principles and to make people think. There we go. Initially, most people say list, of course. I have tried asking that question many times because of the many insertions and deletions. In the middle, lists are good at that. That answer is completely and dramatically wrong. There we go. That's the sentence I was looking for a moment ago. So people tend to say list because you're thinking I'm inserting and deleting from the middle of the thing many times in a random fashion, and that answer is wrong, dramatically wrong. And then, are you familiar with this Stack Overflow question by any chance? I believe it is technically the most popular Stack Overflow question ever, 27,000 upvotes. Why is processing a sorted array faster than processing an unsorted array? Do you know the answer to this by any chance? Branch prediction. Branch prediction is one aspect of this, and cache effects is another aspect of these things. And it's complicated. It's complicated. We've got all kinds of keywords that you can Google for that are related to cache things. We've got direct map cache, associative cache, write-through caches, cache hits, cache misses, cache lines, prefetching. How many levels of cache do we have? Right? We have just all these things when we're talking about cache, and it's a very complicated topic. And our modern caches have diagrams that look like this. This is taken, what machine is this from exactly? I don't know. But we're talking megabytes, gigabytes of cache, depending on the device. We've got level 3 cache, level 2 cache. We've got level 1 and level 2 caches that are shared across cores, and then we've got instruction data caches that aren't shared across cores. It's ridiculous. And associativity. Has anyone seen diagrams like this before? Do you know what it means? Can you explain for me, Klaus? There's a cache associativity. Actually, I don't honestly remember what this means, and I was not joking. If anyone wants to like chime in here, because it's been too long since I studied stuff like this. Maybe this is the kind of thing you deal with every day. Yeah.
A memory address can only fit a certain number of cache slots. Cannot match any cache slot.
Okay.
You can get, if you have 4 access patterns, that you may actually only be able to use a part of the cache because all your accesses only fit in each slot.
Okay, so not every memory address can go in any cache line, so it has to, or in any piece of cache. So it's a question of which chunks of cache can be utilized by which memory addresses. And yeah, so you can make yourself in an even worse situation than you thought you were in. So it's complicated. There's been a few talks about writing code that is friendly to your hardware. I don't know, is any of you in this room at the moment? Jonathan Mueller? No. Let's see. Want fast C++, know your hardware from Timur. Write cache-friendly C++ from Jonathan. CPU cache effects from Sergey. CPU design effects from Jakob. We've got memory allocator talks from everyone at Bloomberg. basically. And Bjorn gave a talk on memory allocators just yesterday, actually. And then we have Bjorn as well. What do you mean by cache friendly? Should I care about my CPU cache from Camille? CPU friendly code from Borisov, I'm guessing. Maybe is that a way or is that a now? All right. Cache warming, how to warm up your cache, how to design fast, efficient, cache-friendly code, cache-optimized hash tables, C++ algorithmic complexity, data locality, parallelism. Like, there's just so many talks about this. Have you seen any of these talks? Have you given some of these talks? I just out of curiosity, does anyone have like a one sentence, like what have you taken away from watching these talks? It's complicated. What do you want to say, Victor?
Always measure.
Always measure. Okay, that's a good one. Anything else? Yeah. Wait, do what, sorry? Oh, if you don't know, then vector and array. Yeah, that's well, that's kind of what I had said too. Yeah, and these giant layers and complexity of cache, this new problem that we're dealing with, I started to think this had like an old familiarity to me. This is approximately my first hard drive. Yeah, Victor.
Speaking of talks, I was surprised I didn't see Mike Acton's CPP keynote on there about data-oriented design.
Oh yeah, for the remote people, Victor is surprised that I didn't put data-oriented design talk from Mike Acton on there. That probably would have been a pretty good one to list as well, but I largely was like searching YouTube for cache keyword and putting together things that I recognized and things I didn't recognize, and I wasn't thinking about that specific talk. Has anyone else had this hard drive? It was very popular. Yeah, go ahead and seriously raise your hand if you had this hard drive. There's only one other person in the room, seriously. It's a Seagate ST225. It's a 20 megabyte hard drive. My first hard drive, or my first computer with a hard drive had 2 of these in it. And they were already quite old when they ended up in my computer because I could only afford used computers at the time. These things mean anything to you? MFM, RLL? No. 8-bit ISABus? Okay. Low-level formatting? Does anyone here actually work in the storage industry? When I gave this in my meetup, I had one guy who had been working at Seagate for like 30 years. So he was like, oh, let me tell you stories here. Interleave. No? Okay. Well, a couple people getting a couple nods. All right. Seek time? Yeah, okay. Now sounds a little bit more familiar. So you have to be, I think, particularly old to know what interleave is about. So we'll cover that in a second. And the little formatting. Let's just pretend like this is my hard drive layout. And I've got tracks. And I've got sectors. The sectors are the things that spoke out. As I'm reading data from the disk, you might read, like, I want to read from 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, right? Like, as the disk is spinning underneath the drive head, I want to read the next chunk of data that's becoming available to me. What happens if your computer is actually slower than your hard drive? You're laughing because you remember this era, right? Did anyone else ever have a computer that was slower than their hard drive? All right, thank you. I'm not alone in the room. Okay. I had my 286 with this hard drive in it. And so you could run tools that would actually calculate the speed of your hard drive and decide what the optimum interleave factor was for you. And you might end up with something like this. You reformat your hard drive so that you actually space the sectors around the disk. And that is because you've got your read head and the drive is spinning and you read this chunk of data, but your computer's not fast enough to read the next block of data. So if the drive passes underneath it, and you missed the opportunity to read it, you have to wait for the next revolution to complete before you can read the next block of data. So we actually space it out so that our hard drive that's faster than our computer doesn't have to keep spinning waiting for us. Some pretty impressive stats here. 3,600 RPM, stepper motor for moving the drive head. They don't, voice coils, I believe, is what's used currently, not stepper motors. 1984 construction, 21 megabytes. Some sweet storage space. Pretty cool stuff. 5 megabits per second. Yeah, all right. 65 millisecond seek time. What's the seek time about? Yeah, moving the head, finding the next track that you're looking for. I have videos and a cameraman. This is the hard drive head actually seeking. So you have lots of questions about how quickly can it find that track? How long does it take to start moving? How long does it take to settle moving before you can actually be ready to start reading the next thing? Yeah, so just Wikipedia page about this kind of stuff. We've got the seek time, rotational latency, how long does it take for the data to come back underneath the head? How long does it take for the drive itself to actually process the command that we asked it to process? And how long does it take everything to settle and be able to read this data? Who currently still uses a spinning disk of any sort? Is it just in your file server? Raise your hand if it's only in your file server. Okay, yeah, that's most of us, I would say, in that case. It's the only place I have spinning disk left. All right, here is a disk mark. Notice the random read times on the bottom. "68 megabytes per second down here. This is greater than 100 times slower than like the best case sequential read times, read throughput. Does anyone notice something that you should notice if you're like really reading the slide? Like why, like, wait, why does he have that slide up right now? It's not a hard drive, this is an SSD. I found this benchmark first accidentally, put it in the slides, and then looked at it later and said, wait a minute, that's an SSD. Even in an SSD, it's possible for random reads and writes to be considerably slower than sequential. If we go to my old spinning disk friend here, then we're talking, and this is not even that old, this is a relatively modern terabyte Seagate, 128 to 586 times slower to do sequential reads and writes across the disk, as opposed to, to do random access as opposed to sequential. I just realized I'm not keeping track of time at all. Oh, it's only been 20 minutes. And we have plenty of time and plenty of slides. All right, so for the best disk performance, we access data in the same order that is laid out on the disk. We access data linearly. We're ready for the data when it arrives. We knew all this decades ago. For those of you who are too young to know what this is defrag. Well, it's not actually defrag. I'll tell you what this is in a second if you don't recognize it. This is what defrag looked like from the DOS 6 era, I would say. That's when defrag shipped with DOS, right? DOS 6? Was it 5? It wasn't 5, it was 6, yeah. All right, so you would actually, from time to time, run a program that would look for all of the files on your hard drive. It would scan through the FAT, and it would say, oh, you know, these files are scattered, like pieces of the files are scattered all over the hard drive. That's terrible performance. And it would recompact those files so that all of their data was laid out linearly on the hard drive so that we had much better performance reading from our disk. And we would choose to manually do this from time to time. Windows does still have a defrag, and it will do automatic background defrags on disk where it matters. It's important to actually, in many ways, not do this on an SSD because you're going to wear your hard drive down faster, or your solid state storage down faster. But, you know, on the spinning disk, we did this. Now, I said a moment ago that I would tell you what this was, since it's not actually defrag. This is, and my pointer is not very visible, but this is a game called ZFrag. It's Zen defrag, I believe, is the point here. This is meant to just be one of these things where you load it up and you are like kind of zoning out, manually defragmenting a virtual drive. And if you just want the old experience, you can click on auto defrag and it will just do the animation for you and defragment the bits here. So if you're curious, it's an actual like itch.io game, ZFrag. You can have the fun old experience of defragmenting a drive. All right. So data access patterns. I'm just going to stand here, take a drink of water until someone makes some sort of a comment. Yeah. It depends on how the data is laid out. So compared to perhaps this, if you didn't notice, I swapped the inner and outer loops, X and Y. Might be better, might be worse. Yeah. Row access versus column access. I remember my intro to data structures class. This was in 97. I have 97 on the slide. I would have sworn it was 96 if you just asked me. Might have been second semester of my freshman year. I remember the professor, instructor actually, mentioning that, you know, oh, on some systems, this can have a performance impact. And then I literally do not remember this coming up again at all in 4 years of computer science after that. And I don't even remember if an explanation was given. So if we've got our data, let's say our array, two-dimensional representation of this data laid out 1, 2, 3, 4, 5, 6, 7, 8, 9, and we're thinking of it as a 3x3 grid. If we do row major access, we've got all the data as it was laid out in memory, because memory isn't two-dimensional, at least on any computer that I'm aware of today. Did like, I don't know, supercomputer companies back in the day do weird stuff like that. If you access it column major, then you're skipping around 1, 4, 7, 2, 5, 8, 3, 6, 9. I mean, this is 9 integers. Is it going to make an impact? No. Who works on data sets that are more than 9 integers? Who, when writing a nested for loop, thinks about this? Now, you do think, okay, all right, cool. Who, when writing a nested for loop like this, doesn't think about it? More people, okay. That's me, just for the record. It's not until I really started thinking about this while I was working on this stuff. So if we access data in the correct order, we get the elements in the order they're laid out in memory. If we access it in the incorrect order, we're jumping around in memory. Yeah, so I already asked you who thinks about this. Magnetic tape reels. Very bad random access seek times. And I love that it has to have actual buffer of tape so the tape doesn't get stretched when it's going back and forth. That's what that little loop of tape is at the bottom there. Yeah, so who's ever actually programmed on one of these systems? You know they still exist. Tape storage is a thing because the density is much higher than anything else that we've got, and cost per petabyte or something. I don't even know at this point what you measure this stuff at. So if you're accessing your magnetic tape in the order that the data is laid out, you get read, 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 read. That sounds nice, right? If you're accessing it in the order that it's not laid out, doing the wrong order, then you've got read, fast forward, read, rewind, read, fast forward, read, rewind. That's really bad. Or if we've got a spinning disk, read, seek, read, seek, read, seek, read, seek, right? So back then, if you will, you couldn't write software if you didn't take this into account. Your program would have been unusable. How did we deal ultimately with this desire for random access while processing data? Cache. Here is a gaming hard drive. You know it's fast and expensive if it's a gaming hard drive. 10 terabyte drive from Western Digital today. 256 megabytes of cache. The hard drive has more than 4,000 times as much RAM as my Commodore 64 had. Here's Ryzen 9 stats. If you sum these things up, see now, when I first gave this talk, someone pointed out to me that there's only 128 megabytes of usable cache, because if something's an L1, then it's also an L3, but that's not the point. The CPU has 145 megabytes of cache on die. This was a screenshot randomly taken from my laptop. It has 32 gigs of RAM. At any given random moment, I happen to have 14 gigabytes of RAM allocated to cache by Windows. I mean, you know, it dynamically adjusts these things. It keeps as much in cache as it can, but we're caching all the things at all the layers. So it becomes not just complicated, but it also becomes risky with things like side channel attacks and meltdown and Spectre and cache contention, data corruption. We've got cache vulnerabilities. It's not good. So it's complicated, risky, and expensive. This is a Ryzen Zen 3 die. It's almost easier to point out the things that aren't cache in your current CPU. I have another little overlay here, but there's something I just noticed closer yesterday. This little green blob, can you see where my pointer is on each of the cores? That's related to cache. And this blob over here that's kind of pink up in the upper corner, that's related to cache. And this little green blob in each one of the cores is related to cache. That's in each of the cores. Do you see this big, giant pink chunk in the middle? What is that? That's cache. That's cache. That's the L3 cache. Each core, set of cores, has its own L2 and L1 caches. It is well over 50% of the cost of producing a CPU is cache. So let's take a linked list and pretend that we either have no cache or perfect cache. This is the capital L list. It's a very, very simple linked list representation that I created. That is iterable, so there is some C++ in the talk. I lied. It's a tiny, tiny bit of C++ here. I do have a I have a ranged for loop over the elements of my list. And I compiled it to 6502 assembly, as one does, of course. This, I do have links to all this stuff in a moment. if anyone wants to check this out on their own. All right, who said they can read 6502 assembly? Okay. All right, so this is just that loop of going through all of the elements in this list. And I tried to comment it as best as I could. We load the pointers of the current element, load the pointer of the list node, get the pointer to value on line 6. Then we call that do thing function, which I explicitly made it out of line so that we could actually see this call to the do thing function. And then it increments the pointer and loads the next offset value from the next node to get the next pointer, and then it loops back through, right? Because that's how a linked list works. I should have people stand up and demonstrate a linked list, shouldn't I? Sorry, that's to my students from Monday and Tuesday. But each node has a pointer to the next element in a linked list, right? So it's having to do this pointer indirection on each element. And this is small, succinct code, but I counted how many cycles it takes to execute, because I can on a 6502. I know exactly how many cycles it's going to take. It's going to take between 49 and 64 cycles per loop iteration. Now I'm really calling you out here. Does anyone know what this 5 or 6 cycles is about? 2 or 4 cycles is about? Yeah, go for it. Carry from the calculation of the address, which is the, crossing a page boundary, or is the other, yes, right. So it's, if it has to like go page bound, like more than 256 or, yeah. So, and there's also an extra cost if you, if your branch is successful, then an extra cycle cost for that. So I wanted to highlight these because the possibility of actually having to pay that extra cost of going to a next page is relatively high, I think, with the linked list. All right. So this is just a span. A span is a pointer into a contiguous array of data, and I'm iterating over all of those elements. And so it's worth, I think, noting that it is like exactly the same number of instructions in this optimized 6502 assembly here, but we're now talking 43 to 57 cycles per iteration, and far fewer instructions that have that actual non-deterministic, at the time of the function execution, extra cost of doing a page boundary. Linked list versus contiguous access. The probability of page boundaries, like I said, I think increases with the linked list, which we might, let's just, for the sake of argument here, equate this to a cache miss on modern hardware. Contiguous access has one less pointer indirection per access. So we're talking 49 to 64 cycles for a linked list versus 43 to 57 cycles per loop iteration. I just see what really got me, like how I ended up here, is thinking about the fact that I started my career by saying, well, list is better because we don't pay these costs for inserts. Now we talk about cache effects in modern hardware and everything. Some of that, is true back then, but just the base case of I need to access this data, if it's linear, it's always been faster. 11 to 13% more efficient or more with fewer page boundary crossings. And I do have an actual compiler explorer link to that. That is the 6502 example. So we used to know this. We used to know that contiguous accesses were better. Why did, now we're at my hypothesis here. We knew this, but we forgot it and had to relearn it. So I'm trying to figure out when we forgot this and why we had to learn it again. So this is a very simplified selective timeline of computing history that tries to prove my specific point. Let's just be honest, right? Like, it's not a complete timeline of computing history here. But in 1980, the Commodore VIC-20 has 5 kilobytes of SRAM. And at the time, so I've got two numbers for each of these prices. They're all in US dollars. Scale will work. The first number is how much RAM actually cost at that particular time in history. The second number is adjusted for inflation. The VIC-20 used SRAM specifically because it simplified the design of the motherboard. With DRAM, with dynamic RAM, it needs a refresh, which means you need a memory controller. On the VIC-20, they didn't have a memory controller available, DRAM controller available that they wanted to pay for, so they used static RAM and only went with 5K of RAM. Static RAM by being much more expensive than dynamic RAM, but it simplified the cost of the overall board. I have read the complete history of Commodore, by the way. It's a 3-volume work. I recommend it. It's on YouTube, but it's quite the tome. Memory at the time, adjusted for inflation, cost $24,000 per megabyte. 1982, the Commodore 64 came out. It had 64K of RAM, but we're in an interesting, very, very brief moment in history here where my RAM was actually twice as fast as my CPU. In 1985, the 386 launched, initially without a cache, and it was a 12 megahertz CPU and 12 megahertz system bus. RAM was clocked at the same speed as the CPU at that point. 1986, my old hard drive, the ST225, can read faster than some system buses, and we talk about interleaving to slow down the drive so it matches the speed of my CPU. Up to this point, RAM is too expensive. So in 1985, it was about $850 per megabyte. Notice, from 1980, $24,000 per megabyte to $850 per megabyte already. But still too expensive, and our peripherals are too fast for our CPUs, for some definition of too fast. Around 86 to 92, things start to change. $300 for $850 per megabyte in 1985. That's what the last slide had on there. 386, right? Carryover from the last slide. In 1986, RAM price is already down to $529 per megabyte. In 89, we've got our first 486 running at 16 megahertz, and the system bus is still 16 megahertz, and RAM is now down to $278 per megabyte. And 90 down to $107 per megabyte. So what is that in 10 years from $24,000 per megabyte to $100 per megabyte? That's a huge change. And 92, we get our first modern desktop processors where the CPU is clocked at a slower, noticeably slower speed than the system bus. Our CPU is now faster than our memory. At $56 per megabyte now we're down to. Then I'd say we kind of fell off the cliff here in the 93 to 2006 timeframe. We've got the Pentium at 60 megahertz, and as far as I can tell, this is the first CPU that had separate data and instruction caches, and a fairly considerable L1 cache. If you consider it wasn't that long ago, the Commodore 64 had 64K of main memory. We've now got 16K of L1 cache on our Pentium processor in 93. I did some research in the Internet Archive, and as far as I can tell, the first mention of the phrase cache-friendly was in 1994, and it was showing up in supercomputing literature, old school supercomputing magazines. See, I didn't have a mention of Java previously, but my members of my meetup told me that I should mention Java here. Nothing personal to the one person in the room I know who's a Java programmer. Java 1.0 came out. And I remember anecdotally, because I was around in this time frame, that's when I started university, that we kind of just expected CPUs are going to keep getting faster and faster and faster and faster, right? You remember that era? Like, there's no end in sight. Soon we'll have 78 gigahertz laptops, right? That was 96. RAM is now only $10 per megabyte. Again, down from $24,000 per megabyte. 1999, this is the first CPU to hit 1 gigahertz. It's the Athlon K75. Had 128K of on-die cache, and the system bus was way less than a gigahertz. And the L2 cache in this particular device, this particular chip, the L2 cache was running at 1/3 the CPU speed. So now we actually have our cache that's slower than our CPU, not just our main memory. 2005, the Athlon X64X2, first dual core. I owned one of those. I had almost forgotten. 2 gigahertz. Just for the record, yes, that's 2,000 times faster than the VIC-20 was. Then Commodore, in 2005, Herb Sutter wrote this article for Dr. Dobbs' journal. It's called "The Free Lunch is Over." Do you remember this? We can no longer talk about CPUs getting infinitely faster. We now have to go to multi-core, basically. 2006, our RAM is down to 11 cents per megabyte. That's 28,000 times cheaper, 218,000 times cheaper than it was when I started my timeline 26 years previously. So this is my hypothesis, that at approximately 2005, we got lazy and we started relying on cache. We said, whatever, I can access memory however I want to. It's fine, it's fast. Everything takes care of the problem for me. This is a historical graph on this. I had to truncate things, but I mean, this isn't like logarithmic or anything. This is like literally just what it did. Like memory was effectively infinite cost and went to effectively zero cost over this time frame, while CPUs speeds were on a trajectory that looked like they were never going to end, but our RAM speed was actually at a much lower slope. So our CPUs outpacing the speed of our RAM, while the cost of RAM is going to zero. RAM prices towards zero, CPU speeds trending towards infinity. CPU, RAM, speed ratios were looking increasingly bad, so we're relying more and more on cache. So we've gone from not needing / not being able to afford cache because our memory and peripherals were faster than our CPU, to absolutely fully relying on cache for anything resembling reasonable performance. I'm kind of curious if anyone, now that I've like laid out my timeline, my hypothesis here, does anyone want to argue with me? Yeah, go for it.
What about people focusing on big oil notation instead of units and stuff? Do you think that's playing a role?
But people focusing on big O notation instead of cache friendliness? Do I think it played a role in this timeline here?
No, in forgetting that linear access is actually.
Oh, the people forgetting that linear access is better. I think it did play a role. I did. That's an interesting point. Victor has a comment there.
Not related to this, but to another factor that I think influenced history in terms of programming patterns.
Yes.
And that was the trend of functional programming languages, which were very much coming up in the early 90s from the inheritance of const cells and just building up lists of
Right.
nodes. So that influenced also some of the programming patterns that people saw in the early 90s.
So Victor's comment was that the rise of popularity of functional programming languages like, yeah, conscoder, because it's
small lists, things out of small lists.
Making list of things had some impact here. I want to also just say, I think, so I did an interview not that long ago where someone said, oh, like we need to do X, Y, and Z. Like what what should you do here in this code interview, right? And I said, well, given that it's hard to directly predict what cache effects and whatever, like I would, consider using a flat map here, and then I would measure the difference. And the person I was interviewing with was like, no, wrong answer. You use a standard map because of big O analysis. And I'm like, but what? You had your hand raised as well, yeah.
That was just a fun fact about the final program pattern, because he said that the cache currently showed up first in around 1994.
That's when I first could find it in literature, was 94, yeah.
At the same time, I saw a line graph drawing algorithm that's written in assembly that still used self-modifying code for branching. It was the last time I saw self-modifying code anywhere. And someone told me that this is a way to screw up the internal cache for CPU. This was completely new to me at that time.
Okay, so the comment from the audience here was around 94 as well, you saw a self-modifying line drawing routine.
Yeah.
Self-modifying code for drawing a line, and you said it was literally the last time you saw something like that because they commented that it would be screwing with your cache on your CPU. Is that correct?
Yeah, maybe because you had the separate instruction data cache.
Yeah, separate instruction data cache. And yeah, like some props to our hardware designers that kind of thing even works at all, right? And they keep all the caches like consistent and everything else. But it, besides that, the branch prediction thing, which I just completely glossed over at the front of this, you're really messing with your branch predictor if you're writing self-modifying branching code. Don't do that. Right. When people thought it was more efficient than doing branching. Yeah. Right.
Well, nowadays, how many tutorials you are going to get that is telling you, yeah, before going to this, just go to your system, learn about it, what is the architecture, how much RAM, how much all of that. It's kind of forgotten when you are teaching someone new about the programming.
So the comment, again, for the video later, was back then in the Commodore 64, you basically had to start with a hardware manual if you wanted to do anything and learn about the architecture of your system, when today you don't do that, basically, right? And no one really starts from that perspective. Is there another? Yeah.
So you mentioned the year 2005. So what was that?
2005.
Well, multicore was the big thing, right? So Universe 4 and everything was really focused on the challenges of multiple programming.
Right.
So they probably pushed cache efficiency.
So your argument is the fact that we're trying to figure out efficient multi-core processing maybe pushed our thoughts about data access patterns and cache friendliness and whatever to the back burner. That might be true as well. I have an anecdote about that as well. Yeah.
Still, when we interview candidates for, say, out of university today, we ask them questions about this search vector and data access. They usually reply with this vector, but can really understand why. So it seems like the default has changed.
Okay.
Cannot really explain why.
So you said fresh university students will now tell you vector should be your default, but they can't really give you a good answer as to why. Yeah, so my anecdote, which I did share with my students earlier because it came up, was around 98 era, I managed to acquire a dual Pentium 2. It was like one of these slot 1 deals, so it was like a lot. NT4 at the time was absolutely terrible about process scheduling. So it would run like on one CPU, and then when it went to do a task switch, it would say, well, this CPU is still busy. So it would swap this whole task over to the other CPU, and then swap the whole task over to the other CPU again. And you could watch it do this ping pong on a long running task, which was absolutely terrible for utilizing the cache on the CPU. And I didn't fully understand at the time why it was bad. I just learned, moving processes was bad, like when I was reading like Linux articles and stuff, but I didn't know why. Okay, so that's where we last left. Okay, so CPU speeds have only doubled in the last 17 years since I left off on this chart, but we have many, many more cores. Interestingly, RAM clocks are actually catching back up with our CPU speeds. And I have to say, I don't really honestly understand enough about modern memory architecture to know exactly what that means, but it's very, very close to CPU bus speeds now. Storage is now attached directly to the system bus, NVMe. Hopefully we all have NVMe. Seriously, if you have a computer that doesn't have SSD or NVMe in it, and you can afford it, it will change your life. Just swap out that hard drive. I promise you it will. I did this for my nephew. He moved in with us. He had a gaming laptop that had a 7,200 RPM disk in it. I'm like, no. Slot the NVMe in. The thing's like 10 times faster. All right, that's all the references for how I got to all this historical stuff, if you want to look at that and argue about it later. So what do? We assume every pointer in direction is a cache miss. Thank you, Bjorn. I have quoted you probably more times than anyone else because of this specific statement. So how do you write cache-friendly, performant, optimizable, and vectorizable code? Pretend like this is your data storage. I am not old enough to have used one of these. It's not a loop, just for the record. This is actually going somewhere. Are you familiar with this device? This is a punched paper tape. It's reading into an Altair, actually. So it's a relatively recent video on YouTube. It's like 10 years old or something. That is, yeah, just demonstrating paper tape reading. What just happened here? What kind of random access do we have to the data on that tape? Zero. No random access. If I were to have missed this byte right here, what would have happened? It's gone forever, right? All right. This. This is a Hollerith punch card sorter. I have also not ever used one of these, just for the record. Oh, I guess it was actually IBM called named at that point. I relatively reluctant to mention this, but I read a book recently called IBM and the Holocaust. It is an incredibly depressing book to read, just for the record. However, there's lots of discussion about IBM punch card machines that come up in that book. And so I realized that there's a direct overlap here to the topic I was already thinking about. So back to Bjarne. Bjarne said this we want to circle. His main takeaway from this whole where do I insert, or what kind of container do I use if I'm inserting and deleting a bunch of things, was don't store data unnecessarily, keep data compact, and access memory in a predictable manner. That's what we have to do. So how do we write cache-friendly code? Pretend like you don't have a cache, and pretend like you can only read the data once. That has been my takeaway from all of these talks and taking the historical perspective here. So how do these things actually help? We have many CPUs. Actually, how many CPUs do you have? How many CPUs is in your laptop right now? 10? I think mine's 8 times 2. I think I've got 16 logical CPUs on this Radeon. I date myself right there. They're still faster than our devices. NVMe, very, very fast. Slower than our CPUs. But fortunately, we do need to do some kind of processing on our data, right? So if our goal is literally to just read the data as fast as possible, we're still going to be faster than our input and output devices today. But if we're doing some kind of processing at all on the data, even if it's just shoving it into another storage device, we're taking some time here. So while we process, our caching infrastructure is going to prefetch and have that stuff waiting for us. So we're still relying on the cache, but we're pretending like it's not there. We're pretending like we just have this magnetic tape we're reading from, and everything will sort itself out in the end. So I think I ended a little bit early, but that is who I am, Jason Turner. I do stuff. If anyone wants to talk to me later, I have stickers up here. And is there any questions before we wrap this up? No other questions? I got you all talking during the argue with me about the historical perspective part. All right, thank you very much.